like chapter, well, I guess like the third week. We don't really do chapters in this class. The measures of center was the mean, median, mode. Measures of variation was like the range, the standard deviation. And then we did measures of position, which is like the percentile, because that tells you where your test score is based on other people's test scores, or where your height is compared to other people's height. So the measures of position tells you where that data point falls along other data points. There's one type that we did not cover in that section just because I think it makes more sense here, but it is technically a measure of position. It is called a z-score. Okay, so let's talk about z-scores for just a second. A z-score, actually, let me just go over here and write it. I don't know why this is out of order. Okay, a z-score, my non-mathematical definition is how many standard deviations away from the mean. How many standard deviations you are away from the mean, okay? So a standard deviation kind of tells you like what the general variation of the data is, and this tells you how many like variations away you are from the data. All right, so the formula for a z-score is x minus the mean, kind of a terrible mean there, x minus the mean divided by the standard deviation. In words, what this is the data value you're looking at, so your test score, your height, your whatever, the data value minus the mean divided by the standard deviation. Okay. This is a very important thing that we use in statistics because what it does is it standardizes all data. Okay. It standardizes all data and makes it one thing. So for example, we're going to talk a lot about this today. But this is the normal curve. Maybe I just need one of these. This is the normal curve, okay? When you have the way you draw one of these out, and it's going to be important to like get the idea behind this. We probably should spend some time on it, tell you the truth. Well, we're going to spend all week on this thing. But the normal curve, the mean goes in the middle, okay? So this is my mean. And then, so for z-scores, if my z-score is how many standard deviations I'm away from the mean, at the mean I'm 0 away, right? I'm 0 away. If I go to the right side, I would add 1, so my standard deviation is 1, or my z-score is 1, 2, 3. So I'm 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. On the left side, you subtract, so it'd be -1, -2, -3, okay? So these are my z-scores. What they would say here is this is the standardized data. Okay, so my mean goes in the middle, then you add the standard deviation. So here my mean would be 0, and my standard deviation would be 1. I add 1 as I go to the right, I subtract it as I go to the left. Okay. What we are going to look at here is what I mean by standardized data. Let's say I took your, shoe size, okay? If my average shoe size was 7 and my standard deviation was, 2, just for easy math, I can plot this on the same graph. I could put 7 as my mean, and then I would add 2, add 2, add 2. I would subtract 2, subtract 2, subtract 2, okay? So I can put a set of data on here. If I wanted to do, Instagram followers. I don't know what my mean would be on this one. I'm just going to put a number out here. What's the mean of Instagram followers? 150. Standard deviation of 20, okay? So this one, I would do my mean in the middle. I'd add 20, add 20, add 20. Here I'd subtract 20, subtract 20, subtract 20. So this is what I mean by it standardizes data. Like the average shoe size may be a 7, but the average Instagram followers may be like 150, okay? But I can put them on the same graph because we can look at this and use our z-scores and it standardizes over there. A shoe size of size 9 would have a z-score of 1, right? Would have a z-score of 1. But also, if I had 170 Instagram followers, I'd have a z-score of 1, okay? So the z-score standardizes all my data, okay? You can say that is this relatively bigger or smaller compared to this? So what I'm talking about here is it more impressive to have a size 13 foot compared to the average? Or is it more impressive to have 190 followers on Instagram compared to the average? Well, 192 would be 2 above the mean, and a size 13 foot would be 3 above the mean. So it's more unusual, or it's more relative bigger to have 13 size foot than it is to 190. So you can compare all these different things to this, okay? All right, so how do you find the z-score? We'll keep talking about that chart, but how do you find the z-score? I gave that formula right there. Chow attends a fashion institute that has no on-campus housing. The mean distance commuted to campus among all students is 19. That's my mean. With a standard deviation of 3. There's my standard deviation. The distance for Chow commutes is 27. This is going to be my x. That's the value that I'm looking at. So again, the formula I'm using is x minus the mean divided by the standard deviation. I don't make you memorize formulas, but you might as well memorize this one because you will use it a lot. Data value minus the mean divided by the standard deviation, okay? So we are going to find the z-score. So we do Chow's distance minus the average distance. That tells us how far we are from the mean, okay? And then we divide it by the standard deviation. So 8 divided by 3 is what, 2.67? So Chow's z-score is 2.67. What this means, it's positive. So you are 2.67 standard deviations above the mean because it's positive. Okay, so he lives further than the average distance. All right. So still on the z-score. What's that, above or below? After, I always kind of already did this, but we can go through it quick. After this year's census of its members, the local pilots association found that its members, why is it not cropping the way I want it to? A mean of 3358. Mean of 3358. Standard deviation of 714. And the census shows that he has 3125. So again, if I was going to label those, this is my mean, this is my standard deviation, that's my x. So z equals x minus the mean divided by the standard deviation. 3125 minus the mean divided by my standard deviation. You just figure out how far it is away from the mean, and then you divide it by standard deviations, and that tells you your standard deviation, or how many standard deviations you are away from the mean. 3125 minus 3558 divided by 714 is negative 0.61. Says 2 decimal places. Okay. All right, so that's my z-score. So Jose's flight experience is 0.61 standard deviations below the mean because it's negative. Okay. So this is the way we talk about z-scores. You don't really use positive and negative. Negative would be below the mean because it's less than average. And positive would be above the mean because it's more than average. More than the average. Comparing the relative size. All right, so this is talking about the standardization of data. Why they got these names? My goodness. Anyone wants to help me pronounce some of these? Inquiry. Okay, N and P. How about that? N and P are social media apps in which, social media apps, at least not people's name. Whatever. Inquiry and Prose are two social media apps in which users can post messages and text. Keisha's last post on Inquiry was 395 characters. That sounds like an X to me. Heather's last post on Prose was 143 characters. That sounds like an X to me too. The character counts for Inquiry, so let's go ahead and write this. It sounds like we're gonna have to do two different ones. Have a population mean of 324 and a standard deviation of 33. So for Inquiry or Keisha, this is Keisha. Keisha's using Inquiry. 395 minus the mean divided by the standard deviation. 395 minus 324 divided by 33. 2.152. Okay. My other one is Heather on Prose. Her X is 143. And for Prose, the mean is 65 and a standard deviation of 27. So obviously, by looking at this, if Keisha's using 395 characters and Heather's using 143, Heather has a lot shorter posts, right? So Heather in Prose was going to be, her X was 143, her mean is 65, and the standard deviation is 27. 143 divided by, minus 65 divided by 27 is 2.89. So my answers here is Keisha's is 2.15 standard deviations higher than the average on Inquiry, whereas Heather's is 2.89 standard deviations higher on Prose. Okay? So actually, even though Heather's posts are only 143 characters and Keisha posts are 395, Heather's posts are longer than Keisha's relative to what's on the platform, right? So this is back when tweets could only be 144 characters, right? Even though it's a shorter message or a shorter post, it's relatively longer than all the other ones on the platform. Does that make sense? So this is what it means by relative, and it standardizes all the data. Now, one thing to note here is this right here. The distribution of the character is bell-shaped. You can only compare z-scores if it is bell-shaped. Okay? We may write that out just right here. You can only compare z-scores if it is bell-shaped. I wonder if I can make this big right here. Heading. You can only... I don't want to do that. I'll bold it. You can only compare z-scores when the distribution is bell-shaped. Okay. So we are only talking, this is called a normal distribution. We'll talk about normal distribution next. Okay. So as I... No. Refresh this problem real quick just to show you. Maybe. Seriously, I'm not going to get one. Oh, my goodness. Oh, man, that was it. And I wouldn't buy it. Now I got to go. Okay. So I'm not going to work this whole problem out because y'all know how to plug in the z-score. We've done it 4 times now. But if I look at this problem right here, it says the salary levels were clearly skewed. Okay? We cannot compare z-scores. So you can find the z-score, but you can't really like compare them because it's not standardized. So your answer is it is unclear who got the higher salary. We can't compare them when you have skewed data. You're going to work this whole problem and skip by that line. It doesn't really show you that. So make sure if it says clearly skewed, the answer to part C or B is it is unclear. All right, what's next? What is this one? I think we'll do this one next. That's fine. Nah, let's do. I was trying to decide if I wanted to do that one today or next time because it kind of goes next time, but we can start it. All right, the empirical rule. Let me copy my chart right here so I don't have to draw it again. Do I want the z-scores? Sure. Should have went and got a pretty picture instead of my handwriting. Okay. The empirical rule is called the 99, 95, 99, 7 rule. It is a standard rule, and we'll kind of talk about on next time how we get this. So the empirical rule, they also call it the 99... Sorry, I just went completely blank. 67, I bet I'm going to double check this because now I've like completely confused myself. Is it 68? I don't know what in the world. I'm losing it. I turned 40 1 week from today, so my brain's just going. 68 and 68. My goodness. Just don't get old, you young people out there. 68, 95, 99, 7. I don't know why I went blank there. I was trying to do 98. Okay, whew. I can have senior moments now. Okay, 68, 95, 99, 7. This is the percentages of the different ones. I'll show you how they find this in just a second. But if you remember way back when we talked about standard deviation, I said like you can take your shoe size plus the standard deviation, and if you add and subtract it, this says that the majority of people wear a shoe size between 5 and 9. Do y'all kind of remember that a little bit? If you add the standard deviation, you subtract the standard deviation, the majority of people wear a shoe size between 5 and 9. Okay? This is where I got that from, is the empirical rule. What this says is that 68% of the people are going to be within one standard deviation of the mean. 68%. So they use a calculator to find this. They use calculus to find it, really, so we just know the numbers. If I go 2 standard deviations away, 95% of the people are within 2 standard deviations from the mean. And if I go 3, it's 99.7% are within 3. Okay? So back to the shoe size example real quick, just because that's on my head, I guess. And you can find pretty pictures of this online if you just Google empirical rule. 7, 9, 11, 13, 5, 3, 1. So if I did like shoe sizes. Mean of 7, standard deviation of 2. Okay, so I could say 68% of the people have a shoe size between 5 and 9. That kind of makes sense, right? How many people have a shoe size between 5 and 9? 4 or 5, right? Okay, so we only got like 11 people in this class, so everybody skipped after the test. But now 95%, I go 2 standard deviations away, 95% of them have a shoe size between 3 and 11. How many wear a shoe size between 3 and 11? Almost everybody in the class, right? So that makes sense. If I go 3 standard deviations away, 99.7 have a shoe size between 1 and 13. We talked about outliers previously. Anything outside of 3 is considered an outlier. That kind of makes sense. Anything outside of -3 or 3 is considered an outlier. All right. So this is kind of what happens here. If you're one standard deviation away from the mean, 68% of people are within one standard deviation of the mean. So the majority of people are within one standard deviation of the mean. If I go 2, 95%. If I go 3, it's 99.7. Okay? So on this problem right here, it says the length of movie files that are available for streaming are modeled by normal distribution. The mean of the distribution is 190.3. I'm going to show you the quick way to do this on the calculator since got it right here. And the standard deviation is 19.8. Okay. They give you blank spots on this graph. Actually, I won't show you the quick way right now. If I take the mean plus the standard deviation, 19.8, does it look like 210 would fall right here where this W is? It does kind of look like 210 would fall right there, right? Okay. All right. So I added it one time, right? Now let's undo it and let's do subtraction. Can I not just go back? I don't have my keyboard hooked up, so it won't let me go back. 190.3 minus 19.8. So I added it once, so now I'm going to subtract it once to see the other side. Does it look like 170.5 would go right there? Yes, it does. Okay, and the mean always goes in the middle. What was it, 190.3? The mean goes in the middle. Okay, so I added it once and it looked like it fit. I subtracted it once and it looked like it fit. So I am one standard deviation away from the mean. So that would be 68% go within one standard deviation of the mean. Okay. I don't really need the calculator. Let me write this real quick. I'll show you the shortcut or the way that I kind of think about doing this, and it kind of helps my brain, but not necessarily just a calculator shortcut. So this is the mean. This is the mean, and then we did 190.3 plus 19.8 and got 210.1, and 190.3 minus 19.8, and we got 170.5. Okay. By the way, I haven't really said this yet, but all data starts to look like that normal curve. It always starts to look like that the more and the more people I ask. Okay. All right, so this one's further away. So if I do 72.7 and I add 5.4, the mean plus the standard deviation, my mean goes in the middle, 72.7. If I added it once, right, 72.7 plus 5.4, 78.1 does not go where this box is right here, does it? Okay, so what I got to do is actually I have to add 5.4 again. Does that look like it could be 83.5? Yes, so I had to add it twice, right? Okay. The shortcut version that I do this is, you can do this, is I could do 7.1 plus or minus 1 times my standard deviation. So if I go one standard deviation away, this will add or subtract it. Wait, will that? Was that right? That's right, isn't it? 72.7 minus 5.4. I was making sure I put it in the calculator right. 67.3 and 78.1. Okay. It does. Yeah, it does. I was making sure it did in order of operations, right? I did multiplication before it did a division. So I did one standard deviation away. So one standard deviation away would be 76.3 and 78.1. That wouldn't be right. Okay, that doesn't fit my blanks. What if so I click undo. Oh man, I can't undo it. And change that to a 2. So now I'm 2 standard deviations away. Does that look like that could be 61.9 and 83.5? Yes. So now I'm 2 standard deviations away. When I'm 2 standard deviations away, I am 95% of the people fall within that range. Okay. So you can either like do it like that, or you could just add it twice. It's probably easier just to add it twice. But that thought process does work. If you're 2 standard deviations away, you can multiply the standard deviation times 2 because you're adding it 2 times. So what we did on this one was we took my mean right here in the middle, and then we did 72.7 plus 5.4. What was that? 78.1, which doesn't work. So we only did plus 5.4 again, which is the 83.5. So we added it twice. You're 2 standard deviations away. Added twice, 2 standard deviations away. Okay? So now you subtract it twice. 72.7 minus 5.4 minus 5.4, and you get your answer 61.9. Okay? All right. The next one is very, very similar to the empirical rule, still using 68, 95, 99, 7. Where's that? That one. Okay, on these ones, it does not hurt when we get our pictures. I'll show you how to draw it out faster on Thursday. But it does never hurt to get in the habit of drawing a quick curve. Okay, so 49 in the middle. My mean is 49, right? Mean is 49. So now my standard deviation is 13. So mean is 49, standard deviation 13. So I add 13. Add 13, add 13. Here I subtract 13, subtract 13, subtract 13. Okay. Doesn't hurt to do that, just to like have the picture real quick. You could probably find a calculator online to do it for you too. But all right, so approximately what percentage of the students scored between 36 and 62? Well, 36 and 62 is 1 standard deviations away, right? So that would be 68%. Approximately what percentage of the students, approximately 95% of the students scored between what? So remember my rule is 68, 95, 99, 7. So 95 is 2 standard deviations away. So 2 standard deviations away would be 1, 2. It would be 75 to 23, 23 and 75. So you have to add the standard deviation twice. Okay. And then, oh wait, that was this topic. The very last topic is kind of the converging into what we're doing on Thursday, but I will do it real quick. So it's very easy to take the mean and add the standard deviation once in your 1 standard deviation with z-score equal 1. You add it twice, z-score equals 2. You add it 3 times, z-score equals 3. You subtract it once, it's -1. You subtract it twice, it's -2. What happens when you start to get into like a half a standard deviation or 0.48 or like these different decimals? We got 2.88 a minute ago, right? So what you do on this one is you graph. You're going to graph to the left of z equals -0.5. So I go to -0.5. They give you the lines right there, so it's very easy to do. And it says to the left, so I'm going to graph to the left. Okay? Now it wants to figure out, we kind of know based on our chart. I didn't make y'all do this, and I should have. I am going to make y'all do this. Can y'all think about this real quick for me? We know all the different percentages from this chart. 68%. 68% between -1 and 1, right? 95% between -2 and 2. Can anybody tell me what percentage is to the left of this right here? 50. It cuts it in half. The mean is in the middle, so it cuts it in half. So there's 50% to the left, 50% to the right. What if I wanted to figure out how much is in here right here? In between like -2 and -1. Actually, answer this question first. How much is between, if this is 68%, how much is right here? Between 0 and 1. What? 34. Okay? So you can actually start breaking down each little category. Can anybody tell me how to, you don't have to actually have to find it, how to find how much is in this one right here? If I know this is 95 and this is 68, how much is in that one right there? Tell me how to find it. You don't have to tell me what it is. 95 minus 68 is 27, but then what do I got to do? I got to divide it by 2 because there's 2 areas. Everything is symmetric here, so you would do that. It'd be 13.5%, 13.5%, okay? So I can say things like if my shoe size was 9, I'm in the 84th percentile because 50% this way and 34% this way. 50 plus 34 is 84%, okay? 13.5% of people wear shoe size between 9 and 11, okay? I'm making the shoe size up. That's probably not accurate. But you can start to see all these different percentages. So what happens? What do we do when they don't fall perfectly like that? This is where we're going to use the calculator. The calculator has a button that does this for us. The probability of the z-score or the percentage under the circle of a z-score when it is less than or equal to. So on this one, we want to know the percentage of the z-score when it is less than or equal to negative 0.5. And we get our answer right there. I'm going to press equal 0.3085, but I'm going to undo it. Okay? So that one's very easy because we just put it in the calculator and get our answer. So you can get your number from there. We write a couple things right here just in case you go back and look at it. This is 0.3085, and we use this button right here. That's it, right? This is at negative 0.5, and we shaded to the left. Because it says that right here, okay? All right. What if let's see. That's to the left, Does it ever do to the right? No, it doesn't look like it, does it? I think I've probably refreshed enough times. Huh. All right, well, let's do one more of these just to make sure. Let's get it right, and then let's see what it gives us. 1.5 to the left, we would do the probability of z. 1.5 to the left would be less than or equal to, right? Pretty easy, not bad. Check it. Let's see what it gives me. Try another. Let's pretend. Not on that one. We already did that one. Let's pretend we are doing to the right. Negative 1, and I want to define to the right. See how well you'll remember just from last week. If I put negative 1 into the calculator, that only gives me to the left, right? So if my left is 16%, how could I figure out what my right is? If I know it's 16% to the left right here, like right here, this is 16%. What has this got to be over here? 100 minus the 16%. So remember when we did binomial and I said, if you want to flip the sign, you do 1 minus, and that flips the sign. Same idea here. I want to do, if I want to find the right side of this one, I can't flip that sign, but if I do 1 minus, that flips the sign, okay? It is going to be the same idea. So it's 84%, 0.84. All right. So when we want to find right or greater than when we're doing this button in the calculator, we will still just flip the sign. I thought that this generated some of those. It doesn't, but we will definitely use that thought process on Thursday. I keep getting my days mixed up. So that's negative 0.1 to the right. This equals, oh man, what was it, 0.84 or something like that? To flip the sign, do 1 minus. Okay, so what that says is that this is 0.16, so 1 minus 0.16, this has to be 0.84. All right. We'll definitely use that concept again and again and again, though.